So atmospheric pressure is the pressure of the atmosphere, right? And variations in our atmospheric pressure create wind and cause changes in the weather. So we can look at different pressure regions. So the meteorologists will look at, oh, this is a low pressure region, and this is a high pressure region. High pressure is generally associated with clear weather, low pressure with unstable weather. And so I'm looking at the barometer that we have here in the classroom, and it's saying that the pressure today is 753.8 millimeters of mercury, and it looks like it's coming down. And so the pressure's going down, so that suggests that maybe we're going to have some interesting weather coming up. Did you ever wonder where wind comes from?
Oh,
Yeah, I mean, like, why would the air just suddenly start moving? Is there a giant out there with a fan, fanning? Let's make some wind, or exhaling or something. Well, it's created by differences in pressure. Right? So if you have a high pressure area and a low pressure area, the air is going to move towards the low pressure area. So that's basically where air comes from. It's going to be a good day. Where wind comes from. So how high you are above sea level also affects the atmospheric pressure. The higher you get above sea level, the lower the atmospheric pressure is, because there are fewer gas particles within a given volume. So here we have an illustration of what looked to me like two mason jars with gases in them. So these little pink spheres are representing the gas particles. Here we have fewer particles in the same volume as this volume, but this is more particles, right? So we can assume that these particles are all, at the same temperature because they're sitting right next to each other. Temperature is a measure of the average kinetic energy of the particles. So on average, these particles are moving at the same rate, at the same speed. In this container, they will have collisions with the container and exert some pressure. But here, with those gas molecules, particles moving at the same rate, because there's so many more in there, there's going to be more pressure, right? More gas particles, more force per unit area. Fewer gas particles, less force per unit area. Does that make sense? So we use pressure differences in breathing. Another place this relates to our physical bodies is in our ears. So you have an eardrum that separates the outer ear from the inner ear. If you experience a change in altitude, a change in atmospheric pressure, you'll be able to feel that something is not quite right in your ear. Let's say you're taking a drive up to Grant Grove. You're going up to like 7,000 feet in elevation. The atmospheric pressure up there is lower. Well, you have air inside your ear, and that can be moved in or out through your eustachian tubes. And then, of course, there's air outside. So when we go up the mountain, then the air outside has lower pressure, and the air inside our ear has greater pressure, and that causes the eardrum to bulge outward until your ear pops, right? And that popping sensation is when the eustachian tube opens enough that it lets the excess pressure out to equalize the pressure inside and outside. Yes?
Is that the same like when you're just like at a regular level, like you just sometimes pop your ear? Does that mean just like sometimes it's always built up pressure?
You can get built up pressure. That doesn't happen to me much at all. I think if you're ill, like if you have any sort of an inner ear infection or something, then you can end up with pressure and you might experience that popping. But it's the same thing that happens when you fly in an airplane. You go up high in the airplane, and the cabin is pressurized Because if it wasn't, everybody'd pass out because there's not enough oxygen to breathe. But it's not pressurized the same as it is down at sea level. And so your ears tend to pop when you go up and pop when you come down. And that's why babies tend to scream on the airplane. They're not doing that just to torture the other passengers. Their little ears hurt, right? And if you have an ear infection, avoid altitude changes at all costs, because when your ear is infected, the pressure doesn't equalize as easily, and everything's all sore anyway, and so it can be excruciating. Yeah.
You said like, for example, when the pressure is, you wouldn't have oxygen, like if oxygen would like enter, or if like your blood wasn't burst, if you didn't have enough pressure to kind of balance out the.
Well, that's a good question. Yeah, so if we're talking about like no pressure, like in outer space, then yeah, there could be all sorts of like really freaky things that might happen, like, you know, cells bursting and things like that. But an airplane, anywhere that an airplane can fly, there is still air. There's still atmosphere. And so I don't think the pressure difference there would be enough to cause anything like that. But yeah, you would definitely not get enough oxygen to remain conscious. Yeah. So then if you come back down the hill, now the pressure is going to be building up on the outside and cause the eardrum to bulge the other way. And again, you need to get your ear to pop. And so this is why chewing gum or yawning or talking, that helps, you know, moving your jaw helps to get that eustachian tube to open up and let the pressure equalize. This is an illustration of a Mercury Barometer, which is the original device that was used to measure atmospheric pressure. And the way this was created was by taking a very long glass tube. It needs to be more than 30 inches long, so it's like a yard long, right? It's very long. You fill it with liquid mercury, and then you invert it into a dish of mercury. And now we have different forces pulling on the mercury. We have gravity pulling the mercury down, and we have atmospheric pressure resisting the mercury coming up in the dish. And so we get a balance between gravity and atmospheric pressure, and we find that atmospheric pressure at sea level will support a column of mercury that is 760 millimeters tall, or 29.92 inches tall. What we have up here is going to be a vacuum. It's not air. There's literally nothing there. Because this tube was full of mercury, and when we turn it over, there's no way for air to get in there. This is just a vacuum. We don't see that if we're like playing with cups of water in the bathtub or something. You can invert a cup under the water and you can lift it up and the water will stay in the cup, right? It's like, ooh, cool. And then you lift it up a little further and then it all gushes out, right? We don't see this vacuum with water because the column of water would have to be about 30 feet tall, 30 meters tall, in order for it to make that vacuum. So atmospheric pressure can support a column of about 30 meters of water. So that's why liquid mercury is useful, is because its density is much higher, and so you can make a barometer that's not so crazy tall. And this was how barometers were made for a very long time. In fact, it was only in the last 10 or 15 years that they took the mercury barometers out of the classrooms. We used to have them back in the corner, and it wasn't a hazard because it was all contained, but you go back there and you're reading how tall is the column of mercury today, and that is the atmospheric pressure. So that's why we have this weird unit for pressure, millimeters of mercury, the length of an element, right? It's how tall is the column of mercury. So 760 millimeters of mercury is the average atmospheric pressure at sea level. If we have higher pressure outside pushing down, then the column of mercury will be taller. And if we have less pressure in the atmosphere, then the column will be shorter. So millimeter of mercury is a unit of pressure. Torr is also a unit of pressure. They mean exactly the same thing. I think the intention was torr is named after Torricelli, who first developed this mercury barometer, and I think that seemed like a more appropriate unit than millimeters of mercury. But then it was probably us educators that are like, no, we want to hold on to that because it really just describes so well how the barometer works, and we really like that. So now we just have another unit, right, that means the same thing. So torr and millimeters of mercury, exactly the same thing. Yeah.
Will we have to memorize the pressure conversion, like the pressure?
That's a good question. Do I have to memorize the pressure conversions?
I know on the 3A exam they made you memorize one of them.
I don't remember for sure. It's on the information about the exam. I'm pretty sure I'm going to give you all of these guys. You will save yourself a lot of time if you remember that 1 atmosphere is equal to 760 torr.
I think that's the one they made.
That's the one that we're going to use a lot. The others, absolutely not. Don't memorize those.
Okay.
Not worth your brain space. But 760 torr is exactly the same as 760 millimeters of mercury, which is exactly 1 atmosphere. This is the table from your textbook showing different units. So in chemistry we use torr and millimeters of mercury a lot, and we also use atmospheres. If you look at weather forecasts, they're going to report barometric pressure in inches of mercury. Pounds per square inch is what the pressure in your tire, your bike tire, your car tire, is usually measured in pounds per square inch, which is abbreviated PSI. Pascal is the official SI unit of pressure, and it is a derived unit. It's a Newton per square meter. Newton is a unit of force, and square meter is a unit of area, so it's force per area. These things are all equivalent to each other. So on an exam, I'll provide pressure units in this form because it takes up less space than that table. We can always do pressure conversions in one step because of how the relationships are presented. All of these things are equal to each other, so you just pick the two that you need, the one that was given and the one you're trying to find. So let's do this example. Your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert this pressure to PSI. This is dimensional analysis. So I've got 30.44 inches of mercury, and I want to find PSI. So I was, let's do this, let's be consistent here. I was given the pressure in inches of mercury, and I'm asked to find it in PSI. So we're going inches of mercury to PSI, one step, one fraction. Inches of mercury goes down here, so the units cancel out. Then I go look at the table of pressure units, and I see that 29.92 inches of mercury is equal to 14.7 PSI. I could convert inches of mercury to torr or to pascals or to atmospheres. I can do any combination of pressure units. So 30.44 times 14.7 divided by 29.92. The calculator says 14.95 PSI. The numbers that are exact for these pressure units are the 760 for torr and millimeters of mercury and the 1 for atmosphere. 14.7 is not an exact number. That only has 3 sig figs, and so that's going to limit our answer to 3 significant figures. And so that's going to round to 15.0 psi. Yes?
Do we have to memorize that conversion right there?
No. The only one that is useful to memorize is the 760 torr is 1 atmosphere, 760 millimeters of mercury is 1 atmosphere. That one's useful because we're going to use it a lot. The psi and pascals and inches of mercury we don't use very often, and so we just look them up. Any other questions?
How is it exact if it was like measured, if it's measured in millimeters before?
Well, that's a good question. How is it exact? So that kind of gets to, well, what do we mean by exact, right? So we're saying that 1 atmosphere is the average pressure at sea level,
Oh, okay.
which, you go to sea level, and that's going to change from day to day. And so somebody had to define or decide what average was.
So it's a definition, that's what
It's a definition.
yeah.
And so then, the average height of a column of mercury at sea level is 760 millimeters of mercury. It goes up and down a little bit, but not like when you go take it up the mountain or something.
Okay.
And so they decided that, well, we're just going to, we'll go to 760.
Call it 760.
760 exactly. Yeah. So these numbers are exact, so those are never going to affect your sig figs and pressures. Yeah. Great question. So the barometer measures atmospheric pressure. A device called a manometer measures pressure of a gas inside of a container. And this is the old-fashioned manometer using mercury. Of course, now we have pressure gauges and all sorts of other ways to measure pressure. But I think it's helpful to look at this because it helps us to understand what we're looking at. So here we have a high-pressure gas, and that's going to be exerting pressure on this side of the column of mercury. And the other end of this U-shaped tube is open to the atmosphere. So this has atmospheric pressure pressing down on it. So we have the pressure of the gas versus the pressure of the atmosphere. So here we see that the pressure of the gas is greater because this side is being pushed down farther and this side is being pushed down up. And we can measure the pressure difference with a ruler measuring the millimeters of mercury difference. To know what this pressure is, then you also need to know what the pressure is outside. And since this is greater, you take that height difference there and you would add that to atmospheric pressure. If the pressure in that container was lower, then the mercury column would go in the other way. And to find the pressure here, you take atmospheric pressure and subtract that difference.